Today I'm going to explain about the periodic table properties, specifically how the table itself tells you about electrical conductivity and or its opposite, the resistance. And that's all based upon the various columns in the periodic table. Now, all of this occurs within the structure of HemiChem, that is, hemispherical longitudinal rings for the subshells. Now, so these subshells are all longitudinal rings. So you have from the nucleus an axis. I call it the extrastatic axis. And so you get sets of odd counts of electrons in each shell. Now, your textbook today probably shows these as clouds, but in reality, each of these are individual electrons in a longitudinal rings. That means at the same axis. It's like it's on a hemispherical globe. Now, everything that I do in HemiChem uses Arnold dot diagrams for electrical configurations. The electrons do not fill partially. There is only full. So there's 1 and 1, so that's subshell S in 2 hemispheres. 3 and 3, that's 6, subshell P, subshell D. But in HemiChem's second rule is that there is, for odd count elements, an equatorial subshell of 3 electrons, or sometimes 5. But basically, this does that. And now let me show you what that does and how it explains 3D engineering for electrical conductivity. You see, if you have 3 at the equator, that's not set up as pairs. These are much tightly packed, okay? And this one and that one become matched. This one and that one become matched. They're called polypairs and create what's called the orbital. However, these 3 are not a paired group, so they stick out further because you're trying to fit 3 instead of just 2. The 3 takes up more space. So these are ready to ingress and egress easily. That's there. That distance for that calculation is called the band gap. Now the standard electron is always in these pairs in each hemisphere, put forward by Pauli. Basically what happens is this electron wants to be as far away as possible from this electron. But that electron is balanced by the 2 forces, the radial electrostatic, attraction in at 1 over distance squared, and that extrastatic repulsion, which basically pushes it back out to the Bohr radius. Okay? But the thing about electrons is that electrons have radial electrostatic, and it's opposite, it's repulsive. That's what pushes this so far away. It does not, though, have this extra 1 over r. Okay, so you're missing 1 over 2d versus the equilibrium cubed. That's the extra 1 over r, 1/8. So that means the net interaction strength for this electron is the whole net here, but at 2x we're missing 1 over distance cubed at 2. So that's 1/8. So the item settles, the strength is 7/8. Well, how do you balance 7/8? Well, by moving the electron out, the 2 of them at 8/7, then those balance and you have radial balance. Now, for the subshell rings though, you're trying to fit 3 in. So instead of it being 1 here and 1 here and that being 8/7, these are a little closer, but at an angle. So this calculation is a little more complex, okay? But we can do this, okay? So if you have, say, the 3, I'm going to do subshell P, since that's 3 times 2 hemispheres. Basically, you're going to have 3 electrons, but we want it to be right in the middle, so I can pretty much divide this into 6. So 360 degrees by 6 gets you 60 degrees for that angle, or 2 pi around divided by 6 again is pi over 3 radians. As a result now, you're going to get the calculation of that Pauli pair would want to set here at 8/7 as I just showed, but this one is going to be at 1, twice as far away, which means it has that easy ingress and egress. So the band gap is 2 versus 8/7. Now, let's see that calculation. If you have this, you have 1 in, then you have an extra 1/2, which is the cosine of that 60 degrees, and the sine then is this, and if you square it, that becomes 2.275, so that's 3. So this distance over here is square root of 3. But of course, that strength is 1 over distance squared between these electrons. The repulsion is 1 over distance squared, so you get back to 1/3 repulsion. Of course, though, it's at an angle, again, 1, 2, 3, and over 2. So that's going to lower that strength from that is in this direction, so that the net result is a repulsion that's only half as strong when you put 3 electrons in a rail. That means the distance settling, again, is going to be twice as far, because twice as far of half that gets you equilibrium. Okay? 1/2 times 2 equals 1. Now, what does that do for the periodic table? Well, actually, it tells you a lot. So you can just look at the periodic table and say, well, those odd counts are going to have lots of electricity. In fact, look here at column 11. Okay? That's an odd count. You get 1, 2, plus 6 more, and 3, and that's copper, and that's gold. These are the electrically conductive materials. It's what we use in our houses and our computers every day. And so as a result, this column, column 11, is the most electrical conductivity there is. Now, that's not the only answer. You also get this 3. Well, if you get 3 electrons, it really can't be on either side. It's got to be 3, again, at the equator. So you get lots of electricity for scandium, and these in column 3. And there's other configurations, all of which feed you back to the Arno dot diagrams. I hope this helps. Thanks.